Assalamualaikum warahmatullahi wabarakatuh. My name is Siti Mashita Binti Harun and my metric number is AE230033. So today I would like to present about the methodology. So our primary goal of this project is to clean the high frequency external noise such as the electrography muscle artifact and random environmental noise that often varies critical heartbeat data. First, we identify the noise source. So we analyze the electromagnetic interface. And the second is the imperfection, hardware imperfection. And the third is the random muscle noise, AWGN, and the 16 Hz hum characteristic for the power line critical hum. And then the second is the select filter architecture. So we choose FIR over than IIR because it's provide the linear phase, which is to keep the exact peak timing and shape of the PQRS peak width without distortion. And then the third is we define the specification. So we set the five order and the cutoff frequency is 40 Hz and the sampling frequency is the 500 Hz. And then second, we design and simulate. So we try to implement FIR filter with the humming window. And second, we verify the performance. We try to analyze the frequency response and the noise attenuation. So they have two reasons why we choose FIR over the IIR because the stability. So FIR filter is really exclusive on the feedforward pass. So which are no feedback loops. And second is the mathematically is guarantee bounded input and bounded output VIVO stability. And the second reason is the first characteristic. So the first characteristic FIR is the linear phase, then it will produce a equal time delay for all frequency components. So it's also successful to prevent the peak timing distortion or smearing of the sensitive PQRST complex. Now let's talk about our filter setting and how they connect to the SP theorem in the MATLAB. So we set our sampling frequency at the 500 Hz, the cutoff frequency at 400 Hz, and the filter order at the 15. So according to the Nyquist theorem, our sampling rate must be more than twice the highest frequency to avoid the overlapping and distortion. Since our heartbeat data is below 400 Hz and the power line noise is at the 60 Hz, our 500 Hz setting easily satisfies this rule. So as you can see on the slide, a perfect brick wall is filter is impossible in real life because it requires an infinite amount of mathematical data to make it practical. So we use the Hamming window. So by doing the math for a 15 order filter, so our transmission rate comes out to 33 hertz. 33 hertz. So how we get the 33 hertz? So the equation is delta F equal to 3.3 divided by the number of order and then multiply by the sampling rate, sampling frequency. So we get the 33 hertz. And this means that our filter start cutting off at the 400 hertz and completely block everything by the 73 hertz. So this mathematically calculation prove that exactly why our design is successful at wiping out the 16 hertz electrical harmony and high frequency muscle noise. So here are the equation of discrete time linear convolution. So Yn is the filter output samples we call as the weight and equal to the sum of the Hk. Hk is the filter impulse response coefficient and multiply by the x bracket n minus k is the current and pulse noise input sample. So because our system is relies on a 15 feed forward coefficient and operate without feedbacks. So the Z domain transfer function is contains only zero. So the mathematically currently absolute Bibo stability. Next, 15 order FIR filter inherently takes times to compute treat a constant group delay. Group delay is the time lag. So we calculate using this formula. N is the order divided by the 2 and we got the 35 sample. To resolve this lag, we program an active phase composition block within our MATLAB workspace by advancing the output array index by exactly 25 during plotting. we completely nullify the processing lag. So the clinical alignment ensure that our filter output match the true time distribute of the biological heartbeat without shifting the medical peak.
Assalamualaikum. My name is Najmi Farha binti Jamil, and I would like to present about the results and discussion for case 1 of our project, critical low signal monitoring. I have included all of the parameters inside this MATLAB script, such as the sampling frequency at 500 Hz, sampling period 1 over 500 equal to 0.002 seconds, and so on. So, after we run this MATLAB script, we could see there are three figures or three waves inside the figure 1. At the very top, we have the targeted ECG signal, which is the clean ECG signal. Even though it is weak, but we can clearly see and identify the PQR, S, and T features. Other than that, this is the exact pattern that a doctor needs to see to evaluate a patient's heart health. In the middle one, we have the noisy ECG signal with 60 Hz interference and AWGN. Once we added the electronic static, which is the AWGN, and the 60 Hz power line hum, our clean signal is completely distorted. The ECG signal is highly distorted, making it clearly impossible to read and identify. And at the bottom one, we have the output signal after FIR low pass filtering. This is after we apply our 50th FIR low pass filter with 40 Hz cutoff frequency. The filter successfully forced down the high frequency noise and wipes out the power line hum. Most importantly, it completely restored the QRS complex while perfectly preserving the critical low frequency of the heartbeat. Okay, the difference is very huge. We could say that this filtering technique is highly effective for real-time biomedical monitoring. And move on to the command window. Okay, we have the dataset 1 SNR improvement from negative 12.05 decibel to 3.88 decibel. This proves that this massive 15.93 decibel improvement mathematically proves that the filter successfully reduced the noise and rescue the patient's heartbeat.
Assalamualaikum and hi, my name is Nur Farwaida binti Norman. My main number is E230005. Next, I will present about the case 2, which is ECG monitoring under high EMG interference. For the parameter, it sets the sampling frequency, sampling period, signal length, and time vector. For the ECG signal, it generates a synthetic ECG waveform consisting of P, Q, R, S, and T wave. For the EMG noise, it creates high frequency muscle interference at 80 Hz, 100 Hz, and 120 Hz. For the AWGN, it adds random Gaussian noise to simulate measurement noise. For the noisy ECG, it combines the clean ECG signal with EMG and AWGN noise. For the FIR LPF, it designed a 50 order FIR low pass filter with a 40 Hz cutoff frequency using a humming window. And for the filtering, it applies the FIR filter to remove high frequency noise from the ECG signal. And for the delay compensation, it corrects the delay introduced by the FIR filter. And for the plot, it displays the clean ECG noisy ECG and filter ECG waveform for the comparison. For the result, it demonstrates the effectiveness of the low pass filter in reducing noise from the ECG signal. The clean ECG waveform clearly shows the PQRS and T wave. After adding EMG interference and AWGN, the noisy ECG waveform becomes distorted, making it more difficult to identify the important cardiac features. After applying the 50 or the low pass filter with a 40 Hz cutoff frequency, most of the high frequency noise is successfully attenuated while preserving the main ECG component. The filter waveform closely resembles the original clean ECG signal with a smoother appearance and improved signal quality.
Assalamualaikum, my name is Nawazna binti Muazzam and my metric number is AE230015. So I will continue with the discussion. So for case 1, a weak ECG signal with an amplitude of 0.3 was corrupted by AWGN and 60 Hz power line interference. As a result, the ECG waveform was difficult to interpret, and after applying the FIR low pass filter with a cut-off frequency of Hz, the high frequency noise was significantly attenuated, and the ECG waveform became much clearer. So the QRS complexes were successfully recovered and making the signal easier to analyze. And this is possible because the 60 Hz interference lies within the filter attenuation region. So in addition, the FIR filter has a linear phase response which preserves the original shape of the ECG signal. So a 25 sample group delay compensation was also applied to align the filtered signal with the original waveform. So next for case 2, a normal ECG signal with an amplitude of 1 and a heart rate of 80 BPM was contaminated by EMG muscle artifacts and moderate AWGN noise. Although the R peaks remain visible, the P and C wave were partially obscured by the muscle noise. After filtering, the high-frequency EMG interference was effectively removed, resulting in a smoother ECG waveform and a more stable baseline. These results demonstrate that the designed FIR filter is robust against both power line interference and muscle artifacts. However, a small artifact can be observed near the end of the filtered signal, where the waveform suddenly drops to zero. So this occurs due to the group delay compensation process, which introduces zero padding at the end of the signal. So the FIR low pass filter successfully improved ECG signal quality by reducing noise while maintaining the essential characteristic of the cardiac waveform. That's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Izzuddin bin Pangeran. My matrix number is CE240099. Today, I would like to present about the conclusion. So, to wrap up this project successfully, simulated a 15-order digital FIR low pass filter using the Hamming window technique in MATLAB for biomedical ECG noise reduction. As you can see, from our result, the primary objective was achieved. We effectively eliminated the 60 Hz power line interface in case 1 and suppressed the blackboard EMG muscle artifact in case 2. From the ADSP perspective, why did we choose a FIR architecture? Because it ensures two main things: absolute BIBO stability and a perfectly linear phase response. This is extremely important to prevent any distortion on the sensitive PQRST complex. Of course, there was a trade-off. The windowing transition introduced a 33 Hz transition bandwidth and a 25 sample group delay. However, we managed to solve this processing lag by applying a manual shifting in MATLAB to synchronize the filter output back with the reference baseline. Ultimately, this simulated framework proves to be highly robust for cardiac signal pre-processing, especially under critical low signal monitoring or intensive patient movement. That's all from us. Thank you.